Okay, angles. So when you first learn about angles, you learn that the way to measure angles is using degrees. And the thing that you learn about degrees is that there's 360 degrees in a circle. Now you might have been wondering, okay, why did we pick 360 as the number? Why didn't we pick 100? Or why didn't we pick 720 or some other number? And the answer is there's really no great reason. It's more that 360 is divisible by a lot of other numbers like 3, 6, 12. It's also divisible by numbers like 2, 4, 8. So if you want to take your circle and you want to divide it into different sectors, you can do that and you can still get a nice degree answer. But of course, that doesn't really matter because you could potentially just express your angles as a fraction, or maybe you don't even have to express your angles as a number. You could just say it's 1/3 of some circle or whatever you choose. So in that sense, it really doesn't matter what the degree measure that we use if we're just assigning the circle a total number of degrees. Because regardless of what measure you assign to a circle, you'll just have some conversion factor to convert between this standard degree and the way that you measure. But this does raise the question of, is there a more natural way to measure angles? The reason why this question arises, first of all, is because we just agreed that 360 was a pretty arbitrary choice. So what is the best choice, so to speak? And that's why we'd be asking this question of, is there a more natural way to measure angles? And the second question is, why do we want a more natural way? So there is a philosophical answer to this second question, and there's also a more practical answer. So the philosophical answer is more that, well, as humans, we've always been really fascinated with math. And one of the interesting things about math is how, even though it feels like you are creating math, like it's a human invention, you sometimes notice that there was this underlying dynamic behind the math where even though it felt like you were creating it, it was really more that you were just discovering it. Like the ideas were already there. It was just us that were sort of taking these ideas and putting it into our own human language. So a very good example of this is the fact that we count things in base 10. Even though when you look at all the formulas, most formulas don't really do a good job when you're dealing with base 10. Formulas involving exponentials, for example. The only reason we pick base 10 is because we have 10 fingers and 10 toes. And so maybe that way it's more natural to pick base 10. But from a mathematical point of view, base 10 is not the most natural base that you use. The most natural base that you use is base E. And the reason for that is when you have formulas involving E, they become very clean with just the exponential constant, Euler's constant, I mean. But if you try to use 10 as your constant or 10 as your base, you also have some extra constant terms that you need to account for that in the formula. So it's the same thing over here. When you have formulas that involve degrees, and this is going to the more practical reason, what you find is you end up with a lot of extra constant terms in these formulas, which really don't have any meaning. And you can make your formulas very elegant and very simple if you use the more natural way to measure angles rather than degrees. And so that's what we're going to be talking about when I have radians as the title of this lesson. So radians are going to be what we call the more natural way to measure the size of an angle. So let's do a little bit of exploration first with angles. Let's say we have a fixed angle. And let's say it has some measure theta. Okay, so theta, you can think of it in degrees, or you can think of it in this future measure that we're going to figure out. But it doesn't really matter right now. It's just fixed size theta. After all, the measure of an angle, like, it's just units, right? We can use degrees, or we can use this new measure that we're going to talk about, radians. It's really just units, because you're still going to be scaling by some factor either way. So let's say we have some angle theta. And now let's talk about the arc length. So this is arc length A, and this arc length is coming from the fact that an angle really just represents a fraction of a circle. So let's say this is the sector that I took out of the circle of radius r and angle theta. And so this sector happens to have arc length A. Now let's look at the sector with angle 2 theta. So we have 2 thetas here. Well, what would the arc length be? It would just be 2 a's, because we have this distance is a, and then we have this distance is a. So together it's 2a. And this is 2 theta, the length of this total angle, or the measure of this total angle. So what you notice is that as you pick your angle, and as you increase your angle by some factor, that changes your arc length by that same factor. So if you double your angle, that'll double the arc length. If you cut your angle in half, that'll divide your arc length by 2. So does that mean that we could just use arc length to measure the angle? And the answer is almost. So there's just one caveat to this, which is that let's say I have an angle, again, let's use theta, and let's say the arc length is A. Now, let me actually give you a fixed value of the radius. Let's say the radius in this case is 4. And then let's look at this angle, the same angle, but with a smaller sector, or smaller radius. Same angle though, theta. And now the radius is 2. So this arc length is A. So it wasn't enough to just look at arc length, because arc length is dependent on the radius. But you can still get around this. And the way you do this is realize that even though the arc length is dependent on the radius, it's dependent on the radius in a proportionate manner. So for example, if the radius is twice as big, as long as I fix my angle, fix theta, then my arc length will be twice as big as this arc length. And so, even though the arc length is not constant, the arc length divided by the radius will be constant. And let's say this is equal to an even tinier circle with radius 1, same theta angle. And let's say the arc length is r. R is actually a bad variable. Let's pick q. So what we've discovered is it's going to be constant for fixed theta. And this is what we'll use to measure theta. So essentially, for any theta, what we'll do is we'll look at the unit circle, and we'll look at the sector generated by that. And then we'll just take this length, q, which is just the arc length divided by the radius, and that will be the number of radians in an angle. So in other words, we say the number of radians in theta So the number of radians, theta, that equals arc length divided by radius. And if radius equals 1, that's just the same as the arc length. So the number of radians will be just the arc length. And now when you use radians to define your angle, to measure your angle, a lot of these formulas that you'll see later on, they'll be very simple and elegant. So the next question is, how do you convert? So how do you convert between degrees and radians? So first, let's figure out how many radians there are in the full circle, because we know that there's 360 degrees in the full circle. So if we know that, then we have some comparison to go by. So let's take the full circle, and we could take, we can take an arbitrary radius, or we could do a circle of radius 1 and just compute the circumference. But right now what we'll do is we'll just take circumference and then divide it by radius. So remember, radians so the angle that makes up the full circle, that equals circumference of the circle, because that's arc length of a full circle, over the radius, r in this case. Now the circumference, well, you know the formula for that, that's 2 pi r. So when you divide it by the radius, that's just 2 pi. So in other words, the radians of a full circle is 2 pi radians. And we also know that a full circle has 360 degrees. So now when you put this together, let's say you want to convert from degrees to radians. Well, what you would do is you would say, okay, let's say I have some amount of degrees. Let's say it's x degrees. And we'll just use our standard dimensional analysis. So you take x degrees and you multiply by 2 pi over 360 degrees. And so by your dimensional analysis, the units cancel out and you're left with x times pi over 180, and that's the number of radians. Now let's say I want to convert from radians to degrees. Well, I'll again use dimensional analysis. So I have, let's say I have r radians. Well, I know that there's 360 degrees for every 2 pi radians. So again, cancel the units. And I'm left with r times 180 over pi degrees. And there you have it. So let's look at some examples now. So convert 90 degrees to radians. Let's first just reason it out, and then we'll use these formulas, of course. Well, 90 degrees is 1/4 of a circle. And In terms of radians, well, 1/4, so a full circle is 2 pi radians. So 1/4 of that should just be pi over 2. And let's actually compare that with what we get. So let's do 90 times pi over 180. And indeed, we do get pi over 2. Okay, let's look at one more example in the other direction. So now we're converting radians to degrees. And again, before we use the formula, let's just reason it out first. So you know that 2 pi is 360 degrees. 2 pi radians is 360 degrees. So that means pi radians is going to be 180 degrees. And then pi over 3 radians should just be 180 divided by 3, or 60 degrees. So let's check. The pi's cancel, and you're left with 60 degrees. Okay, and that's all for this lesson. So I have some more exercises for you to try out. It's just a couple practice problems with converting something from radians to degrees and then degrees to radians. So you can check it out in the handout. And the next lesson, we'll talk about extending our trig functions to bigger angles beyond just 90 degrees or pi over 2 radians. So I'll see you then.